with our derivatives like this, right? Just make sure we're like applying this in the right form. If I'm looking for the derivative, y dash dy dx, like whatever notation you want to use, they're both like equivalent, right? So we keep the constant there. In this situation, what we want to do is we take the derivative of the inside part. So the derivative of, sorry, I lied. You actually do need to know year 11 differentiation for this. You need to know how to remember how to derive like 7. Oh, what do we get? Exactly right. Okay, so if there's just a single power of x, we just get the constant there on the numerator. Okay, and then on the original, on the bottom, we keep the original function there. Hang on, that looks pretty familiar. That's just -1 on x. So as it turns out, right, like if you change like the constant here, like the coefficient of x, you're actually going back to the same function when you take the derivative, okay? So that's like an interesting observation to make. What is a bit different is when you like do stuff like this, because now this time you've got constants there and things will change on the denominator there, right? Kyle, for this one out, what's my original function that I'm looking at inside the brackets? Right, and what's the derivative of that, do you remember? Yep, because like this is a constant goes away. Yeah, exactly right, and then this guy would just be 3. And then we keep the original the same, so 3x plus 4. Okay? Not too bad. Yeah? Even for this one, what's my original function, my f of x? In the brackets.
I want to say 4 plus x.
And you'd be right, yeah?
But
what do you think?
3.
Okay, with the 3 there, like if you have constants multiplied, right, you can always leave them. Okay. When you have to be careful is if you have something like this. Why do you have to be careful of something like this?
Because that's being differentiated too.
Well, but yeah, because this is in terms of x, and this is in terms of x. These are actually two things multiplied together. Yeah, so if you have two functions multiplied together in terms of x, then you have to use different rules, right? Which we learned in year 11. But if it's just a number multiplied by something, then that's fine. You can leave that.
Isn't that like the fx to the power of 3?
Okay, so that's also an interesting observation that Eve has made, yeah? Using the log laws, which is very important when we're looking at differentiation of logarithmic functions, okay, we can often apply log laws. So as an example, she said, hang on, isn't this also this? Right, because if there's a coefficient, well actually usually it's written like this and then you bring it down as a coefficient. No reason why I can't go the other way. So, I mean, you've written this form, we might as well try writing this form, right? What's our original function now?
4 plus x squared to the power of 3.
Yeah, 4 plus x squared all to the power 3. Okay, so that goes on the denominator. That's our f of x. And what would go in the numerator? This is a bit trickier. How do you derive a function like this? 3.
Oh, we're going to use that stupid.
Okay, so be careful of this one, right? So this is called chain rule. Okay. So keep the original the same. We still decrease the power by 1. And then you multiply by 2x there. You can simplify that out as well.
Oh, I see. Oh, man.
Okay, so that's the following problem.
And actually this kind of simplifies out, doesn't it?
Yeah, and then 6x over.
Like, yeah, you just get 6x over 4 plus x squared.
Yeah.
That becomes 1 power 1. So 6x on 4 plus x squared. Let's see what happens if you don't do that, right? Over here, what are we going to get?
But you can also write log, like, e, that stuff, as like 3e to the power of...
Oh, okay, and then take the derivative in the exponential form. That's true. Let's just go back to this one though. Right. If we didn't write it in that form, what would be the f of x in this situation? Yeah, so our original function is just 4 plus x squared, yeah? And what did you say the derivative was, Eva? Laura, sorry, 2x. Hang on, wait, what? Hang on, that's the same as that, right? Yeah, so with the log laws, they can help you, but they can also be a bit of a roadblock or a bit of a detour, depending on the situation. It's not always clear cut. It's not always going to be like, yeah, always write the log law in terms of that. Generally though, like as a rule of thumb, if you like get rid of powers and stuff, that's going to make your differentiation a lot easier. As Alora found out, like all you have to do is just take the derivative of this, that's just 2x. Yeah? Much easier than having to use chain rule for something like this. Yeah? But just to be aware, you actually do in fact get the same thing. So I think that's an important realization to make, that like the stuff that you know is consistent. Yeah? Try for this one now. I've kind of getting away, I didn't plan on doing that, but like this one here, if we were to use our chain rule, we can see that we're going to run into some problems. So maybe have a go at rewriting it in a different way. Okay. So I think highlight an example from this one here is that you can use the log laws to make your derivatives a lot easier, right? Just looking over here, right? Because you remember that, in fact, if you bring the power down there, it means that you don't have to use the chain rule to take the derivative of this, right? So we're going to get, before you take the derivative, right, you should actually write that you're changing the form of this. And then Eva, when you took the derivative, what did you get?
I got 15 and then 3.
Okay, so keep the constant there. Here's our function. Put that in the denominator. The derivative of this guy was 3. And you said you got 15 on 3x minus 7. Woohoo! That's what we get.
Now that's cool.
Now this is pod racing. Right.
Now that is
Emily, next one. I don't know. How'd you get that?
Because log A of x
Yeah.
is 1 on x
Okay.
times n
Yep.
is 1.
Okay. But remember how I said you have to be careful with these ones? Okay, because like with this one over here, this is, you're right in like what the derivatives are respectively. That's fine. Yeah. But remember how this one's just a constant multiplied by this, so you can kind of just like treat it, right? But if it's two functions, just like how do you look for two functions? What you have to do is you have to like notice that they're both in terms of x, and they're two different functions. Right? That's how you know you have to use product rule. Like you've got two things multiplied together. So product rule was u times v, where you have two things. And then, like, if you like to, you can always draw up that table, right? So u is equal to x, u dash is equal to 1, which is what Emily said. And then v is equal to x, and then that's 1 on x, right? So then we have to apply our product rule.
What the hell? That's so dumb. No, it's not.
So now, Emily, what are we going to get? If I have u dash plus uv dash, we can just match it up, eh?
Yeah.
So what do you get?
Log A of x.
Yep.
Sorry.
But then what about this part?
Plus 1.
Yeah. So you were close, right? Funnily enough, right? There's a 1 there. But you should be careful that you're actually applying the
So why does it just move up by
chain
1
rule.
on it? Just like the graph's like my derivative is
But then this is x times log e of x, right? So do you want to have a look at it, or?
now.
Okay. That's pretty cool. It just shifts up by 1, eh? That's an interesting observation, actually. I kind of want to look at it now. So you can see that the gradient's actually negative at some point over here.
Log e of x. What the hell?
And then the black one is our derivative function there.
Yep. You sure it's right? Yep.
Yeah. Because at some point it gets 0, the gradient's equal to 0.
Log e the x looks like that.
Because it's the inverse of our exponential function, right? So if you graph them together, let me just show you.
Can you say f of x equals to the first one?
What do you mean? Sorry.
We'll just like check the
Oh, check the derivative graph.
we got it right.
F dash of x. Oh, I know, plus 1. There you go. Yeah.
Yeah.
Yeah, nice.
What does Cooper do? What do we do?
Yeah, we can have a go. Yeah.
So we back in mine.
2x minus 3.
Yeah, because derivative of this guy, 2x minus 3.
Yeah, is that full thing?
That's it. X squared minus 3x plus 1. So with log functions, actually, like once you recognize the form, they're pretty good to differentiate if these forms are easy, right? You just have to be careful of stuff like if you have weird things like this, you can use product rule, or maybe sometimes I'll put in like fractions. If you have your fraction inside there, you have to use, might have to use quotient rule. There's some tricks and things you can do though to make it easier, but we'll show you next lesson.